So now that we have the first of our new methods for finding the roots of a polynomial in place, right? That's what we're still focused on, finding the roots. Let's see how we can use this thing, right? Let's walk through some examples. So this is kind of the most basic application of the factor and remainder theorems. And I've got a polynomial, 3x to the fourth plus 2x squared minus x plus 2, and I want to know, is it divisible by x minus 1? In other words, is x minus 1 a factor? Now, I see students a lot of times, they get this, oh, okay, divide, right? And they do polynomial long division, synthetic division, whatever your favorite method for doing that is, and that can get, it's not as hard, but it's a little messy. And we've got this remainder theorem, and the remainder theorem makes this so simple. Remember, the remainder theorem says x minus 1 is a factor if p of 1 equals 0. So that's all I have to check, right? What is p of 1? Well, p of 1 is 3 times 1 to the fourth plus 2 times 1 squared minus 1 plus 2. That's 3 plus 2 minus 1 plus 2. Let's see, 5 minus 1 is 4 plus 2 is 6. That's not equal to 0. Therefore, x minus 1 is not a factor. And that's the answer to my question. That's all it takes. No division necessary at this point. So take a look at this one. Pause the presentation for a minute. See if you can't work this out. Then start it up and we'll go through it together. Okay, so the first thing you have to be aware of, the factor theorem, the remainder theorem, they're very specific in their language. They say the remainder, we're talking about remainders here, right? So we'll do the remainder theorem. The remainder when p of x is divided by x minus a is p of a. Now, I don't have x minus here in my example. I have x plus, and I got to make that look like x minus something, and that something is the number I'm going to put into the polynomial. Well, x minus 2 is x plus 2, so this is my a. So I'm going to evaluate p of negative 2. That's negative 2 times negative 2 to the third plus 2 times negative 2 plus 5 times negative 2 minus 1. Let's see, this first term, that's plus 16 minus 8 minus 2. Yes, minus 4 minus 10 minus 1. Whoops, I lost an exponent there. This was squared, which means that should be plus 4. And you see, now I got to double check. Minus 2 to the third minus 2 squared minus 2 minus 8 times 2 is plus 16. So this should be plus 8 minus 10. There we go. 16 and 8 is 24. Minus 10 is 14. Minus 1 is 13. And there's my answer. The remainder is 13. So again, the wording here is a little different, but these are all playing off the same single idea. How can I tell if something is a root or a factor? And one thing we need to do here, we need to be clear about the relationship between roots and factors. So if I have a polynomial like x minus 1 times x plus 2 equals 0, to find the roots, I set the factors equal to 0 and solve these equations. X equals 1 and x equals negative 2. So notice the relationships here. If x equals 1 is a root, then x minus 1 is a factor. And if x minus 2 is a root, then x plus 2 is a factor. So I need to know this because my factor theorem, my remainder theorem, they talk to me about factors, not roots. So the question here is x equals 1 a root? Well, the question I'm going to answer is x minus 1 a factor? Because they're the same question, right? So now this one I could answer. All I have to do is calculate p of 1. That's 1 to the 4th plus 2 times 1 to the 3rd minus 2 times 1 minus 1. So let's see, that's 1 plus 2 minus 2 minus 1. And yeah, that's 0. Excellent. X minus 1 is a factor, which means x equals 1 is a root. Okay, now before we go on to the next question, I want to stop for a minute and I want to look at this one a little deeper. What does this tell us about the factorization of this polynomial? Well, if x minus 1 is a factor, then x minus 1 has to go into the original polynomial evenly. So let's do that. Let's divide it out, right? I'm going to do p of x divided by x minus 1 and see what we get. You can do this whichever way you like. You can do synthetic division, just regular long division. I'm going to do, let's see, I've got 1. My coefficients are 1, 2. Now I've got to put a 0 here, right? You notice the x squared term got skipped, but I have to have a number here for every term. So you can think of there as being a plus 0x squared in here. Minus 2 minus 1. Let's do our synthetic division. Bring down the 1. 1 times 1 is 1. And add down. 2 plus 1 is 3. 3 times 1 is 3. 0 plus 3. 1 times 3. Add these together. Minus 2 plus 3 is 1. And it came out just like we expected it to. 1 times 1 is 1. The remainder here is 0. And yeah, this was actually a nice confirmation that x minus 1 does in fact divide this evenly. And when it does, what we get back is x to the 3rd plus 3x squared plus 3x plus 1. Okay, but now look, multiply both sides by x minus 1. Right? Multiply by x minus 1. P of x equals x minus 1 times x cubed plus 3x squared plus 3x plus 1. So now you see how we can take this a step further. Once we have a factor, we can kind of divide it out, if you will, and that gives us one step in the factoring process, right? That's going to be a key component, right, of graphing these things, right? Of going from just kind of the standard form polynomial to the factored version based on the results that we're seeing from these new methods. All right, so let's try another one here, right? Is x squared plus 3x plus 2 a factor? Well, now we've got a little trouble, right? Our remainder theorem and our factor theorem, they only work for linear factors, x plus or minus something. They don't work for bigger things like this. But okay, here's what I'm going to do. Right? This thing here, I know how to factor. This is x plus 1 times x plus 2. And now I'm going to use the same kind of principle that I use for talking about numbers. Right? The only way 6 divides something evenly is if its factors do, if both 2 does and 3 does. Well, that's what I'm going to do here. I'm going to check, I'm going to see if this factor divides it, and I'm going to check and see if this factor divides it. And if both of them do, well, great, then their product does. All right, so let's see. I'm going to check P of, and be careful here, right? Negative 1. This is negative 1 to the 4th, 2 times negative 1 to the 3rd, plus 5 times negative 1, minus 1. So let's see, minus 1, minus 2, minus 5, minus 1. That's not 0. All right, and that's enough. Don't do more work than you have to. x plus 1 is not a factor, and if that doesn't go into the original polynomial, then that number times something else is not going to go into the polynomial. So my answer here ultimately is no. That bigger polynomial is not a factor of p of x. Okay, so that's the factor and remainder theorems, right? And I mean, these are great because they give us a tool that we can use to really quickly answer the question, is this a root or not? Okay, the problem is finding the numbers to test, right? Where did I get x minus 1 from in the previous example? Where did I get x plus 2 from? Right? How did I know to test those numbers? Well, that's what we're going to do in the next couple of lectures. We're going to talk about another really important, really powerful tool, the rational root theorem, which is going to give us a way to get these numbers that we can test. And then we're going to talk about Descartes' rule of signs, which is a tool we can use to narrow. Sometimes that rational root theorem is going to give us a fairly large list. Descartes' rule of signs is a tool that we can use to narrow down that list. So ultimately, all of these tools are going to work together. We're going to use the rational root theorem to get a list. We're going to start testing those numbers using the factor and remainder theorems. And as we go along, Descartes' rule of signs is going to let us cross additional numbers off the list, narrow it down even more quickly.